Welcome to this explainer. Today we're going to dive straight into the invisible rules that govern literally everything around us, from your daily commute to epic feats of space exploration. I'm super thrilled you're here because we are going to decode the very architecture of motion.
So imagine you're sitting in a moving car, right? And the driver suddenly slams on the brakes. You instantly feel your body lurch forward. But why exactly does that happen? Or take a totally different scenario. Think about a huge rocket launching into the utter void of deep space. How can it possibly move forward when there is literally nothing around for it to push against?
Well, the answer to that everyday car mystery, and honestly, the whole secret to interstellar travel, lies in three incredibly simple principles developed over 300 years ago. Yep, we're talking about Newton's laws of motion. These laws form the absolute foundation of classical mechanics. They literally transform physics from just a loose collection of random observations into a precise, predictable mathematical framework.
Let's look at our roadmap for today's explainer. 1. The rules of motion. 2. First law, understanding inertia. 3. Second law, force and acceleration. 4. Third law, action and reaction. 5. Newton's laws in space. And finally, 6. Why these rules matter.
Okay, Section 1. The rules of motion, the foundation of classical mechanics.
Every single engineering system in existence either moves or it resists movement. Because of this, engineers have to answer some pretty critical questions. Things like, how much thrust does a rocket actually require? How much braking force is needed for a vehicle? Why does a satellite just stay in orbit? Or how does a robotic arm move with such crazy accuracy? Well, Newton provides the foundational math for all of the above. Whether you're trying to escape Earth's gravity or just build an assembly line robot, you are relying on the exact same rules.
Moving on to Section 2. First law, understanding inertia, the resistance to change.
So what does this first rule actually say? The crucial point here is that a stationary object stays stationary and a moving object keeps moving unless an external force actively swoops in and changes its state. This stubborn property, this resistance to any change in motion, is what we call inertia. And basically, the more massive an object is, the more it absolutely refuses to change what it's currently doing.
This perfectly explains our car mystery from earlier. Your body wants to just keep maintaining its forward motion until the seatbelt acts as that external force to safely stop you. That is inertia in action. It's the exact same principle that lets a hockey puck slide super far across the ice because of low friction. And, incredibly, it's what allows a spacecraft to just glide effortlessly through the frictionless vacuum of deep space for months on end without ever firing its engines.
Section 3. Second law, force and acceleration, calculating the change in motion.
Now we get into arguably the most important equation in all of engineering mechanics: force equals mass times acceleration. It tells us precisely how much force we need to change an object's speed based entirely on its mass. But simply, if there's no force acting on an object, its acceleration is zero. But if you want a larger acceleration, you'd better be ready to apply a much larger force. Heavy objects demand more force to get the exact same acceleration.
Let's put that into perspective. Think about two satellites. Satellite A has a mass of 100 kilograms, and satellite B is a hefty 1,000 kilograms. If both of these vehicles use the exact same thruster force, that lighter 100-kilogram satellite is going to accelerate so much faster than the heavier one. This mathematical reality is exactly why massive spacecraft require such absolutely enormous launch rockets to get off the ground. You have to overcome all that massive bulk with an incredible amount of force.
Let's jump to Section 4. Third law, action and reaction. Forces always occur in pairs.
You've definitely heard this famous phrase before, right? For every action, there is an equal and opposite reaction. But the real key to understanding this is realizing that forces don't just magically cancel each other out. Instead, they always exist in pairs. It's kind of like how your foot pushes backwards on the ground so that the ground can push you forwards. Or when you're swimming, you pull the water backwards and the water pushes you forwards. You literally can't have one without the other.
So back to our space question. How on Earth, or rather off Earth, can a rocket move in the vacuum of space when there's nothing to push against? The answer is, it actually pushes against its own high-speed exhaust gases. The rocket's engines produce hot gas and throw it backwards at extremely high speeds. Those exhaust gases push backward, and because forces always come in pairs, the rocket experiences an equal and opposite force pushing it forward. It's absolutely brilliant.
Right, on to Section 5, Newton's laws in space, the cosmic application.
These three laws are operating simultaneously across every single phase of a space mission. Think about the massive engine thrust needed at launch just to overcome gravity. Or orbit, where gravity is continuously acting as an external force to change the direction of the satellite's velocity, keeping it circling Earth instead of just flying off in a straight line. Then you've got orbit raising, where thrusters increase velocity to change the orbit entirely, and even docking or attitude control, where tiny, controlled forces produce incredibly precise accelerations and rotations. It's all Newton.
Let's ground this with a super cool real-world engineering example. Imagine a CubeSat, a tiny satellite, equipped with a tiny propulsion system that produces just 0.1 newtons of thrust. To put that into perspective, 0.1 newtons is roughly the weight of a small apple resting in the palm of your hand. I mean, it's a practically microscopic amount of force.
Now you might be thinking, that tiny thrust sounds completely useless. But actually, because the CubeSat has a mass of only 5 kilograms, engineers use Newton's second law to calculate that applying this continuous tiny force over several hours will significantly alter its entire orbit. It perfectly proves that you don't always need massive fiery explosions to move through space. Sometimes you just need steady, calculated force applied over time.
Finally, Section 6, Why These Rules Matter. The enduring legacy of mechanics.
That CubeSat example beautifully highlights a core engineering truth. Mastering Newton's rules is what allows us to conquer the sheer vastness of space. We do it by accumulating tiny, calculated forces over long periods. These laws are the absolute bedrock for advanced subjects like orbital dynamics and spacecraft navigation. Without them, modern engineering simply wouldn't exist.
So, as we wrap up this explainer, remember this. Motion is never some random, mysterious thing. It's a highly predictable architectural framework governed by inertia, force, and paired reactions. And engineers leverage this framework every single day. Whether they're designing a suspension bridge, a commercial aircraft, or the next rover bound for Mars, they are using these exact 3 laws to guarantee success.
I want to leave you with this final thought. Newton's true genius was realizing that the mundane and the cosmic share the exact same rulebook. If the same mathematical rules govern a falling apple in an orchard and a multi-billion-dollar orbiting satellite, what other incredible, invisible laws of the universe are just waiting out there for us to engineer? Keep looking closely at the world around you because everything follows the rules.